Hello, I'm Walker Khan, and this is Lab 1, Charge Tapes. Our initial goal for the lab is to simulate charge imbalance with pieces of tape. We've attached our tapes onto surfaces and subsequently removed them to control its electron count. Afterwards, we analyzed its behavior with other objects, such as our hands, books, other pieces of tape, among others. Ultimately, we want to illustrate our observations into physics and programming. As mentioned earlier, we want to monitor the behavior between our charged pieces of tape with other objects. However, we also want to measure whether our tape gained or lost electrons on the charge. Before we continue, we need to state some essential principles. To the left is Coulomb's law, which quantifies a force between charged particles, as well as mathematically demonstrate that opposite charges attract while like charges repel. Next, we have Newton's second and third law of motion, which helps calculate a force value given mass and acceleration, and states that every force has an opposite force equal in magnitude and opposite in direction. Some other principles include an object's inability to exert a force onto itself, and charges not able to be created or destroyed, only transferred. Upon completing the procedure of charging the tape, I began with the initial physical experiments. The results are on screen. According to Coulomb's law, when objects attract one another, they share a negative electric force. This indicates that the charges, our Q values, have opposite signs. The inverse is true when the objects repel each other. A few assumptions had to be made before developing our mathematical model. We acted as if entire pieces of tape were point charges, and that each charged piece has its net charge evenly distributed, ignoring other lurking variables such as air resistance and room humidity. The data in our calculations derived from the model shown in Figure 4. Here we declare that the other tape from Figure 4 will have the y component of its force equal to 0. This is due to its momentum remaining constant during the procedure. Following Newton's third law, we state that a gravitational force counters the electric force between two pieces of tape. We then use Newton's second law to determine the magnitude of these forces, given our initial measured values. We use this data to calculate the charge of the tape, which I found to be 1.5 times 10 to the negative 8 coulombs, the number of atoms on the upper tape, 4 times 10 to the 17 atoms, the deficiency, due to the charge being positive, of electrons on the upper tape, 9.375 times 10 to the 10, and the ratio from electron to atom, which is 2.34 times 10 to the negative 7. I then replicated this data into GlowScript. The same mathematical principles apply to the code, as seen on the left. The right contains the output of the code. It contains a digital free body diagram similar to that of my written work, alongside the results of the electrical and gravitational force and the charge Q value. From our calculations and observations, we can derive that our two pieces of tape have positive charges. This is represented through our positive Q values and knowing that an electron deficiency yields us a net positive charge. As for an earlier test with the charged pen, we now know that it is negatively charged due to its attraction with the charged tape. Now, this leads us to a few questions. What if protons and electrons switched roles as to who's negative and who's positive? How would that affect our data? We know that our magnitude will remain the same, but our signs will be inverted. If this change were to occur, Coulomb's law will still yield the same results. Two charged particles of tape will repel, and charged tape will attract a charged pen. Now, why should we limit how long we handle charged tape? Electrons want to maintain a state of equilibrium. Areas with an electron surplus want to distribute to areas with normal or fewer electron counts when possible. Areas with an electron deficit, such as charged tape, want to gather electrons from sources where there are more electrons, such as our hands, with the motive to neutralize its charge. Thanks for watching.